you know, you have a generic polarization and a primitive class, you get a projective hyperkähler manifold, and its dimension will be, you know, the Mukai pairing of V with itself minus 2, right? Isn't it minus 2? So this can be
plus 2, yeah.
Plus 2. Oh, sorry. Yes. Okay. Thank you. So the point, I mean, the only point of writing this down is that you could get examples of hyperkählers of arbitrarily high dimension, of course, even dimension, because they're hyperkähler. And then, of course, the more general picture would be that you consider the moduli of Bridgeland semi-stable complexes. And this is again for some generic stability condition. Sigma. And you know, as I'll explain, this is not just a sort of random, sort of arbitrary increase of the generality. This is actually a very important part of the perspective on this subject that's developed over the last 10 years or so. But the bottom line is that basically you have this, you know, stability condition, this sort of space of stability conditions, Bridgeland stability conditions. It's a complex manifold, and if you fix your Mukai vector, so if you fix the characteristic classes of the complexes you're interested in parameterizing, then the stability manifold will have a sort of, you know, wall and chamber decomposition, and as you vary the stability condition, you'll get, you know, different moduli spaces, you know, will be constant inside these cells, and then as you cross these real codimension 1 walls, the moduli space of semi-stable objects in that with that Mukai vector V will sort of undergo a discrete change, and in some cases it fits into this picture. It's a flop of this kind. Anywho, so the theorem is that if X is a projective, if X is a projective manifold with trivial canonical bundle, and it's birationally equivalent to M, so I'm sort of fixing all of this data, then its derived category is equivalent to the derived category of M. So yeah, so this is the, you know, it's a nice, it worked out nicely because you get, this is like sort of the first example of like a complete birational equivalence class in dimension bigger than 3, where the D-equivalence conjecture is known. Although I should say that actually, like a special case of this was observed by Donovan and Nick Addington, that actually there are specific cases, particular Mukai vectors, where there are only two different birational models, and that they differ by an explicit kind of flop. So actually, this is, in a way, this is a generalization of their work, although it's a bit more complicated in this generality. So so I do want to say a little bit of the philosophy, or I guess the pieces. There are a lot of pieces that go into this. So there's an analogy with Bridgeland's theorem, which is basically that the way that his thing really worked was that, I mean, there's an analogy in a couple levels. So first of all, the flop. So the sort of crucial thing for his approach is that the flop has a modular interpretation. Oops, sorry. You know, in actually, so it's a cool construction where you know, in his theorem, he actually constructs the x prime, the flop of a threefold. So you have a sort of a curve contraction from a threefold, and you construct the flop as a moduli space of certain objects in the heart of a T structure that's not the usual T structure on dB of x. And so he constructs this moduli space, and then the equivalence is given by a Fourier-Mukai kernel, which is just the universal object coming from the universal object on the product of x and x prime coming from this modular interpretation. So, yeah. So in his picture, it's very, very central, and that's of course what's sort of happening here. So, the other piece is that from the sort of the global version requires the MMP. So namely, you know, he can construct a single flop as a moduli, as a sort of variation of stability in some sense, although that's not actually how it's formulated. But you can think of the passage from x to x prime as a kind of variation of stability, and some moduli of complexes on in this category dv of x. But then that just gets you one flop, and then you need the MMP to say that you can get from two birational equivalent threefolds via a sequence of flops where all the intermediate things are smooth. And that's just not even true in higher dimensions, that you're forced to encounter certain singularities. So already, you know, the approach is complicated for that reason. Right, but the point is that in the case of, so sort of both of these both of these work nicely. In our case, for M, because it's a sort of theorem of Byron-McCree, from maybe 2013 or 2012 or something like that. That in the above setup, so x is actually isomorphic to the M sigma prime for some other stability condition. On the same surface. And I should say implicit that this generalizes. So for Giesecker semistability, there is a particular, for any particular primitive class, there's a particular stability condition such that these two moduli spaces, the Giesecker semistable sheaves, are just the Bridgen semistable complexes in that class. And so basically, oops. So a lot of the inputs that Bridgen needed were actually already in place for these kinds of moduli spaces. So basically, you just have to consider the DBS, and now you move along a path from one stability condition to the other. And the question is, as you go from one stability condition to the other, most of the time the moduli space is the same, but then sometimes it undergoes these sort of discrete wall crossings or changes, and then you just have to now track what happens at the derived category as you cross one of those walls. And those wall crossings, just by this theorem, have a modular interpretation. And so both of those things are crucial. Okay, are there any questions? So I'm going to give you I'm not really going to go that much more into this sort of theorem, because I'd like, as I mentioned, to give you to talk a little bit about derived categories and some of the sort of derived category machinery that goes into this. This will actually be a special case of a more general theorem. So are there any questions before I talk about that? Okay, so okay, so I'm going to go back a little bit. There's a group of ideas that I've been developing for a while. So let me just fix the setup. So G will be a reductive group, V will be a linear representation, and L will be something in the equivariant Nernst-Savary group of V tensor with R. And that's just a fancy way of saying I take the weight lattice of the group and I tensor with R and I take the W invariant piece. So I mean, there aren't that many line bundles on a linear representation. So anyway, so this is going to be our GIT parameter. And without actually explaining what GIT is, because that would not be helpful if you haven't seen it before, but GIT provides a G-equivariant open semi-stable locus. So it's some open thing. And the GIT quotient that is this V semi-stable of L mod G. So, and when I do this quotient thing, I always mean a stack, because I think that's the only quotient. When I want the space, I'll use a double line. So the GIT quotient stack, and then the GIT quotient space, I'll typically denote like this. And the key point here is that for an unstable point in the vector space, in other words, unstable meaning not semi-stable, so there's a canonical, somewhat canonical, it depends on L, and actually secretly it also depends on a norm on the weight lattice of, on the co-weight lattice of G. But anywho, so for an unstable point, there's a canonical map from A1 mod GM to this quotient stack V mod G. And you can, with F of 1 being the same as X. So really you can think of this as an equivariant map. Really, this is just a co-character and an equivariant map. You can also call F to V. Yes. So this is a result of Kempf, and I can restrict this to 0 mod G, and I'll call this thing Gur of F.
Does it correspond to Harder-Narasimhan filtration?
Yeah. Yes. In the modular examples, it is the Harder-Narasimhan filtration. Yeah. Yeah. Or if it's quiver, if this is a presentation for some moduli of quiver varieties or something like that, then it's always the Harder-Narasimhan filtration. Right. So, but anyway, so this is a graded point. It's this map from BGM, from point mod GM to V mod G, is really just up to some natural equivalence. It's a point in V. It's a co-character of G, and then a point that's fixed by that co-character. And I'll call such graded points that arise as this sort of associated graded of a Harder-Narasimhan filtration. Now, because someone asked, I'll give myself permission to use that language. I'll call that L canonical. So I have to give you one more definition before I state the categorical curve on surjectivity. So basically, for any graded point, so in other words, for any co-character and a point that's fixed by that co-character, can you see my mouse when I'm hovering, by the way? Yeah. Okay. So then I don't have to highlight this. Great. So I define this number eta, and it's just a fancy way. I mean, so this is some kind of intrinsic way. I take this map BGM to V mod G. I pull back the cotangent complex, and I take the positive piece. So in other words, it's a complex on BGM. So I can just take the positive weight piece of every homology, let's say. This category is semi-simple. So I take the positive weight piece, I take the determinant, and I take the total weight of that with respect to the GM action. But that's just a fancy way of saying is that I have this point X, and I have, oops, sorry, this is, I have this point and I take the, oops. How did that happen? Wait, hold on, this is not even the right talk here. There we go. So I take that point and I take all the positive lambda weights in the cotangent space of that fixed point, and I subtract the sum of the positive lambda weights in the dual of the Lie algebra. That's a number. It's just an integer. Okay. So the categorical Kirwan surjectivity theorem, which is a sort of a reformulation of a theorem that was in my my thesis actually. So it goes you know, way back. So basically, let's consider the full subcategory of G-equivariant complexes, coherent sheaves on V that has this property. So for every L canonical graded point, I can pull back the complex to BGM, and then it just is a direct sum of its weight pieces. And I want to say that the only non-zero, non-vanishing weight summands lie in this interval. So delta here is again is a sort of fancy way of saying it's a weight basically of the group in this case. You know, tensor with R. So I can ask, what is the weight of that thing with respect to the co-character defining the graded point? But this is a nice kind of invariant way to say what's going on. And so basically I say, so this subcategory that lie in this interval, then the theorem says that this is a full subcategory of the equivariant category, and the theorem is that for any L, if you take a generic delta, this restriction functor is an equivalence. And I should say, I'm not going to tell you what is generic, but I'm going to say example would be if I just take delta plus TL for, you know, so if I take just a really small t and I perturb delta in the direction of L and delta live in the same space, right? They're both in this narrow and Severi group. That would be generic. So there are generic deltas for this theorem, right? So this is a sort of very clean reformulation of a more general kind of thing that you know. Well, maybe I'll mention a little bit, but
Dan,
yeah.
Can I just on the definition of L canonical points? You had them earlier when the map from BGM where one goes to an unstable point.
Yes.
Is that still in the definition, or are you allowing any?
Yeah. Okay. Yeah, one goes to an unstable. So it's basically an L canonical graded point is any point that's the associated graded of some Harder-Narasimhan filtration. It's the nature of Harder-Narasimhan filtrations that that when you have any point will also be associated graded of its own Harder-Narasimhan filtration. Yeah, so there you could also just define it to be that way. You can define it that way as well.
Thank you.
Yeah.
And can I ask, why is this? Why is this theorem about surjectivity? So, what is surjectivity in the theorem?
Right. So it says that there's a functorial. It says that the restriction. So this is really, you know, I have this sits inside of dB g of v, and there's my restriction functor. And so this functor is always essentially surjective on objects, but it's not. That's not a very nice kind of surjectivity. So this is saying it's functorially. I mean, it's split. It's a split surjection. So you have this restriction map, and this equivalence gives you a lift, a functorial lift from the semi-stable locus to that. In particular, if you take any additive invariant of DG categories like Hochschild homology or periodic cyclic or K-theory, the restriction map from dB G of V to dB of G of V semi-stable will be surjective. It's actually a direct summand. And so that's Kirwan's theorem Kirwan's surjectivity is that theorem for the usual equivariant cohomology. So this is like a sort of generalization of that to it's like a non-commutative motive version of Kerwan surjectivity.
Daniel, can I also ask, why did you set it up for linear actions? Because we're kind of used to applying your thesis for like smooth projective over affines. I guess
just because no, I mean it's this theorem is ridiculously general. In fact, this theorem is what's called a theta stratification. Anytime you have a theta stratification, it's just that it's not quite it doesn't quite, the categories, the G categories don't quite have this form. But the linear case, just because that's all I need, I guess. Yeah, for what I'm about to say. Yeah. Right, because so basically this is sort of a version of what I did with my thesis, but then, so V, I want to specialize now when V is what's called a quasi-symmetric linear representation. So here, by definition, I mean, so you have the weights of V, let's call this like beta 1 through beta n, and they live in the character. This is the weight lattice. And quasi-symmetric means that if I take any L, a line, the sum of the beta I, if I take the sum of the beta I that lie in that particular line, this is equal to 0. That's the this is the definition of, this is what quasi-symmetric. So examples, the only one that actually is going to be relevant here is self-dual. So V is isomorphic to V dual. Although it's more general than that. Although it's kind of a strange thing. So this notion is introduced by Schpenko and Vandenberg. Oops. Uh-oh. I feel like I'm not going to get in capitalization right. Anyway, apologies if he's out
No,
there.
it's correct.
Okay. So, and the Schpenko has an accent that I can't remember also, but anyway, so they introduced this notion in the context of what I'm about to tell you. So if V is quasi-symmetric, then you can define this other category. So the key observation here is this is like a cool thing. It has applications, whatever, but it's not, the left-hand side and the right-hand side both depend on L. But something magic happens when you in this quasi-symmetric case, which is that instead of considering just L canonical graded points, I can define the same category, the same thing. It's literally the definition. I just copied and pasted, but it's now for all graded points. So this is the same thing. I can just say. So this is a tremendously more constrained category. In particular, I can have all different L's and I'll get all different GIT quotients. And this is saying that you can take the L canonical graded points for all possible GIT quotients, and you can ask that the weights lie in this interval, and this W via delta will sit inside of all of those categories. And so the theorem that myself and Steve and Sam was that for L and delta generic, so there's obviously containment here because all I did is I added more constraints, more graded points. And the theorem is that when L and delta are generic, this containment is an equality. And in particular, if you combine this with this previous theorem, which says that the G category, this G category is always equivalent under restriction, that tells you that this W category, this magic window category, is also equivalent under restriction. And so now the left-hand side, I've sort of said it, but let me just have it in writing here, that the left-hand side of this equivalence does not depend on L. And so what you end up with is you get derived equivalences for all possible generic GIT quotients. You get derived equivalences that way. And so, yeah, I'm not, if you want to know exactly what generic means, I can tell you, but in particular, I should mention that there doesn't always exist a generic L. This applies in situations where there's like, a T stable point, basically, when there's a T, yeah. So it's a special situation where there actually is a generic L. And in that situation, the generic L, the semi-stable locus G will act with finite stabilizers. And so these, in that case, you get derived equivalences between Deligne-Mumford stacks or orbifolds.
Yes,
and this is also,
sorry, can you please say what exactly the generic L means?
Okay, so I guess in this situation, yeah, okay, so I can define this thing. So this is, I'll define this as a polytope, and it's like the hull of the weights of the character of the exterior power of V. So so this sits inside the weight lattice tensor with R. And the condition is, an L, as I've mentioned, is in MRW. It's the violent variant real weights. So I guess L, so first of all, sigma of V should span MR. That's basically the same as saying that they're generic, the torus acts with generically finite stabilizer, and L should not be parallel to any facet of sigma of V.
The first condition does not depend on L, right?
Right, yeah, I have to, yeah, the first condition does not depend on L. Right, this is the situation. I mean, I think there's a version of generic which, anyway, yeah, this is the condition. The first condition does not depend on L, and then L is not parallel. So it's not a foregone conclusion that such a thing exists. Like you can take T star of like sim.
So if the first condition is not satisfied, then there is no generic L, right?
Then there's no generic L. Yeah, I mean, yeah. If the first condition is not satisfied, then basically the whole thing has this generic stabilizer. The whole thing will sort of be a reductive gerb over something where this condition is satisfied. I think so. There's a version you can say something when this first condition is not satisfied. But it's not, yeah, but just for simplicity, let's just assume this condition is satisfied.
But anyway, this is not the condition, this is not the property of L, this is the property of V probably.
Right, that's a property of V, yeah. And this is the property on L.
Is this equivalent to the usual condition that there are no strictly semi-stable points, or is this something stronger?
I can't remember. There's, this implies that there are no strictly semi-stable points. But I can't quite remember if this is equivalent to the condition that there are no strictly semi-stable points with respect to the torus, I think. Yeah, if memory serves, this is equivalent to saying that there are no strictly semi-stable points for the torus action, maximal torus action on the vector space. But don't quote me on that. We wrote a little bit about this in the paper, so you can refer to that. And then for delta, the generic, so that's what L is generic. Delta generic means so I can take this Minkowski. So let me call this this minus, there's a Minkowski difference. I don't know if that's even a thing, but I'm calling it a thing. It's the points where the Minkowski sum of that point plus this sigma of G lives inside of sigma of V. It means that delta plus nabla, the boundary does not intersect the lattice. So this is the genericity condition on delta. Is basically you have some polytope that you translate around with delta, and any time that the the delta plus the polytope does not hit any lattice points on the boundary, that's what it means that delta is generic. So actually, if you think about it a little bit, there's a hyperplane arrangement. Genericity is the cells of some hyperplane arrangement where the hyperplanes are parallel to the faces of this polytope. Yeah. So there's kind of more to this theorem than what I really want to get into. Like, this gives you a derived equivalence, but there's actually many derived equivalences depending on delta. So for every delta, you get a derived equivalence via this. I take the derived category of one GIT quotient, I lift to this window category, and then I restrict to the other GIT quotient. That's really what goes into this equivalence here. And so that depends on delta. And if you combine this, you get an interesting sort of, you go from one to the other and to the other, you get an interesting representation of the fundamental groupoid of a space that's supposed to be the complexified Kähler moduli space of the GIT quotient. Supposed to be. That I said is probably, I think is probably the complexified Kähler moduli of the GIT quotient. I don't even know what that means, but it's the thing whose fundamental groupoid is supposed to act via autoequivalences of the derived category. So anyway.
Dan, how explicit is that derived equivalence?
Well, I mean, it just depends. Like, before I started working on this window stuff, like the standard for what is an explicit derived equivalence is given in a Fourier-Mukai kernel. And you can characterize the Fourier-Mukai kernel uniquely here, but you can't, I don't know what it really means to write it down per se. So it's not really explicit in that way, but it's like super explicit in the sense that if you want to know what happens like on K-theory, like what does it do on K-theory, then it's like super explicit because basically, like you have this polytope that's like floating around. So, in some small examples, maybe it'll be a hexagon, and then you have a bunch of lattice points. Okay, and let's say you have, like I'm sort of now I'm drawing like a GL2 kind of picture. So you have like let's say this is the weight lattice of GL2, and you have some representation. So the polytope will look like this, and you'll be sliding the polytope up and down. And the point is that as long as there are no lattice points on the boundary, then you get if you take representations, the irreducible representations of G, whose character fits in this polytope, as long as there are no lattice points on the boundary, then those things, will give you a basis for the K-theory of the GIT quotient. And so what you want to know what happens as you move from like here, what happens when you move from here to so you'll lose a couple lattice points like this, and you'll gain a few more lattice points, et cetera. So you'll lose a few lattice points, you gain a few lattice points, and basically you can figure out exactly what happens, how to write the new basis in K-theory in terms of the old basis. Basically, there's like sort of explicit change of bases matrices that you can figure out in K-theory. So if you combine that,
and are there explicit resolutions?
Yeah, based on explicit resolutions of unstable strata. But it's like there's a whole theory of this, like that's very combinatorial basically, because it's Jerzy Wayman has a whole book about resolving these generalized nil cones and stuff like that. So So there's a whole like, you know, it's honestly, it's not exactly my cup of tea. I mean, you know, I think it's cool that it exists, but I'm not like the most facile with this kind of stuff anyway. But basically, if you're inclined combinatorially, you can write down very explicitly what the generators of this fundamental groupoid action do on K-theory. So in some sense, it's very explicit. You can say exactly which bundles go to which bundles, but it's harder to write down a Fourier-Mackay kernel.
Very cool, thank you.
Mm-hmm. But when you say that there is no explicit kernel, does it mean that it is hard to write it down, or does it mean that you just didn't try?
Well, I mean, I don't know that it's hard. The only way that I know to write it down, there might be a very clever way to write one down, to like sort of, but the only way that I know to write it down is to basically use the theorem. So you like go to the product and you want to find something that lies in the window category, you know, so you know, V mod G times V mod G, and then you want to find a complex that extends the diagonal and lies on the window category in both things. And so that should exist. And technically there's an algorithm to find it. So in some sense it's algorithmic, but it involves choosing an arbitrary extension and taking these kind of functorial cones to push the arbitrary extension of the diagonal into the windows that you want. Does that make sense? So basically I can characterize it uniquely and I can give you an algorithm that to sort of generate it. But I don't have like a nice, beautiful, like Bailenson kind of resolution where you'd be like, oh yeah, like here it is. I don't have that, but maybe it exists.
Thanks.
Mm-hmm. Okay, so now that's the smooth thing. It's very nice because it's simple. But you know, for this application, we have to get a little bit more, you know, interesting. We have to get a little more sophisticated. So I want to talk a little bit about the next step from, so this was around 2016, 2017, 2018. I can't remember when it actually was published, but it was around then. And so maybe it was 2016. But anyway, so now let's do the first one step away from smooth is quasi-smooth or a complete intersection. So basically I'll tell you about, there's a situation where you have a smooth algebraic symplectic manifold with a reductive G action. And then you have this thing called a moment map, which is a G equivariant map to the dual of the Lie algebra. And I can define my reduction to be, I take the derived zero fiber, and then I take the quotient. So this is like a mildly singular derived algebraic stack, but it's not all that fancy. I mean, I'll show you a generalization what I mean here. So a generalization of this picture, the one that's relevant for us, is that if you have let's say you have a smooth affine G scheme, I'll give you the following definition: a weak co-moment map. So it's a G equivariant linear map along with an isomorphism between the cotangent bundle of this affine scheme and a G equivariant isomorphin in the tangent bundle. So basically it's a diagram like this where the vertical arrows are isomorphisms, and it doesn't actually have to commute. It only has to commute if you restrict basically to the zero. So this mu mapping G to R is really a map from, is the same thing as giving a map from spec of R to G dual as a scheme. So this is the algebraic version of this picture right here. And the usual moment map, in the usual moment map, phi 1 is the identity and phi naught is induced by some algebraic symplectic form. And this is the definition of what is a moment map. But here I'm just gonna ask that, and this commutes. But here I'm just gonna ask that phi 0 and phi 1 can be arbitrary, and this whole picture only commutes after you restrict to the zero fiber of the moment map. So with this picture in mind, you can basically do the same thing. You define the reduction to be, so this is what I mean when I say derived zero fiber. I mean, I take my ring of functions and I just adjoin this vector space, formal variables in homological degree 1 or cohomological degree -1, with the rule that the differential of any element of the Lie algebra is just the value, is mu of that element of the Lie algebra. So this is a commutative differential graded algebra, and it's G-equivariant. And so this is all I mean. So it's the R spec, it's the derived spec of this mod G. So it's a what they call a quasi-smooth derived stack. So the key fact here.
So is it correct that if the fiber of the moment map has expected dimension, then this is just equivalent to the fiber? Right.
Yes. So that's a general, that's a thing that this causal complex, if it has no higher homology, it's just the same thing as saying mu inverse of Z. It's the structure sheaf. It's R mod R dot mu of G. So if this has no homology, then it's a resolution of its H naught, which is just this right here. And so in that case, it's just equivalent to the H naught. So you have some singular complete intersection. Yes, and then there's nothing derived going on. Which actually, honestly, that might be the case in the examples that I'm considering, but it still is convenient to, I never want to say necessary, but it's still convenient to use to think of it as a derived object for reasons that I won't really be able to get into. But anyway, this thing has I'm still in green here, I want to be blue. So this thing, this cotangent complex has an explicit presentation. It's sort of G, you have the, so this thing here, this is the cotangent complex of X mod, of spec of R mod, so X mod G. Let's say X is spec of R. And then what happens when you go to the mu inverse of G is that you get your mu here. So this is the action map. I forgot to, yes, that's the action map, the derivative of the action basically. So, and then here you goes to OX tensor G, like that. Now, why is that? Anyway, d mu. So, sorry, why am I? Oh my gosh, because everything's backwards here. So this is d mu. Sorry, my parity check wasn't lining up here. So you have the action map, the differential of the action on cotangent bundles goes in the opposite direction. So you have this, so this is the cotangent complex of the quotient stack X mod G. And then when you have this extra obstruction space coming from the fact that you're taking the zero fiber. So this complex, if you just look at it, is self-dual. I mean, kind of. It's constructed so that it's actually self-dual. And that's, if you just flip the order, and by definition, Tx is isomorphic to omega x. So when I dualize this complex, I get something that looks basically the same. And in fact, it's self-dual as a perfect complex on X.
This is essentially the definition of the moment map, right?
Yeah, it's like I sort of have rigged the definition of the co-moment map so that when you do this thing, you get something with a self-dual cotangent complex. And in fact, sort of the theorem is that one of the key theorems is that I'll state it here because I'm running out of time anyway. So a theorem is that if X is a quasi-smooth, let me just say, is a derived stack with self-dual cotangent complex, and X classical has a good moduli space. So this is like, so in other words, there's sort of X, so this is an intrinsic formulation of what it means to have a GIT quotient. So this is like locally, well, then I can actually just state the theorem. Then locally over X, X is isomorphic you know, then let me just say this thing. Then there's a sort of a tall like this. No. Yeah, and so in other words, after base change along a tall map here to X, that's the same as that will give you an Étale cover of X, which has this form. So Étale locally over the good moduli space, these weak comoment maps are, you know, any stack with a self-dual cotangent complex looks this way. So this is basically a local model. It's a quotient, but it's a local model for any stack with a good moduli space that has a self-dual cotangent complex.
I'm sorry. Is X in the theorem is the same as it was before? Is it the same?
No. No.
Ah, that's different.
No, okay. Like script X is any.
No. I'm not asking about script X, but I mean this good.
No. Oh, sorry. Good moduli space. No, this is the moduli space. So a good moduli space for a stack is a map from a stack to an algebraic space, which is Étale locally the map. You know, this is locally the map from spec of A mod G. So this is a theorem, a recent theorem of Alper, Hall, and Rude, that there's a formal definition of good moduli space, but basically it's saying that.
I understand that. The question was just, was it the same X as before?
No, it's different. Yeah.
And the second question is, what is X classical? What's that?
X classical is the underlying. So if you think, you know, this is a derived.
Just H0, right?
Yeah, it's just H0. Yeah.
Okay. Thanks.
Okay, so that's why I've told you about this, is because these are local models. These are the local models for the kinds of stacks that I'm going to be, you know, interested in. Okay, so.
And is it some version of Étale slice theorem?
Yeah, this is a version of the Étale slice theorem, but the crucial thing is that it's modified for the input is this theorem. So there's an input that the Étale slice theorem like this, but in this case, if you have LX, if you sort of fix an isomorphism between LX and its dual, then there's a way to choose these slices so that they actually have this kind of canonical form. So, you know, it's just sort of yoga. So the picture here is that X in our example, so X will be equal to the moduli, the stack of sigma semi-stable complexes. Just jumping back to the application here. In dB of S for sigma non-generic. So I mentioned that if you take the if you have generic bridge instability condition, then you take the moduli of semi-stable objects, and that's going to be a projective manifold. That's a little bit of a lie. You have to do a process of what's called rigidification, but it's roughly it's a GM gerb over a projective manifold. But if you have non-generic stability conditions, then you have a true stack. You know, it just sort of is what it is. But you can show that it has a good moduli space. And the point is that then you can use this result to say that for the non-generic stability condition, Étale locally, you have this nice form.
Can Can I ask, why is it a derived stack rather than just a stack?
So let me see. I don't know. I mean, maybe honestly, maybe Arend knows better than I do, but if these moduli stacks are always LCI, but I have no reason to know that a priori. But basically, it's the stack of objects in dB of S that has self-dual cotangent complex. So it might be that it turns out that stack actually classical, but the actual thing that is the nature gives you a self-dual cotangent complex is the derived stack of complexes on the K3 surface S. So that thing has a self-dual cotangent complex, and then that self-duality is very useful. I mean, that self-duality is used to get this local model. So you can think of this as, it's like it's a version of, there's like various results along the lines of that, locally a variation of stability conditions on a K3 surface looks like a variation of stability for Nakajima quiver varieties. And so this is a version of that. Instead of working formally locally over Y, I'm working Étale locally, but at the expense of having my local model is a little bit floppier than this is not literally a moment map for coming from a Nakajima quiver variety picture. It's something a little bit floppier. It's like some kind of deformation of that or something like that. It's like it looks like a moment map to first order or something. But I don't know. I mean, that comes from this description of this as a derived stack. There's probably there are better answers as well, having to do with some of the stuff that goes under the hood that I'm not going to tell you about in terms of how this theorem is proved. So, but specifically you consider the Harder-Simhan stratification of this derived stack, and even if the stack is classical, it can happen that the strata themselves are derived. The correct sort of structure on the strata the structure sheaf has higher homology. Yeah, so the derived nature of this, you sort of can't avoid, at least from this approach, you can't really avoid the derived nature of these moduli stacks. That was sort of the point of the paper, is that if you allow yourself to work with derived stacks, you get a lot of the theorems, the sort of general machinery becomes a lot cleaner. And then this is one application of that fact. Okay, so I guess I'm sort of out of time, but that's okay. I mean, we had a nice conversation, because isn't this supposed to be an hour, right, Aaron? Yeah.
Yes. Yeah.
Okay. Well, I'm out of time, but we've had a nice conversation, so I don't regret anything. But I'm not going to tell you about. And let me just summarize maybe in a sentence. So I've already sort of given you a hint, but basically the way that this proof goes is, so you have this local model, and you can study the flops. You can study the variation of bridge instability as now you can turn it into locally over the good moduli space for the non-generic stability condition. It looks like just an ordinary variation of GIT quotient for stacks of this kind. And so you can ask yourself, how do you study stacks of this kind? Well, so in the local model, there's this trick that goes back to Ezek and has been used in many times in this literature, which is basically to convert some complete question about a complete intersection, dB co of a complete intersection, or a derived complete intersection in this case, to the category of singularities for some hypersurface. And so basically locally there's a picture, locally there's a causal dual picture that's much easier to work with technically. So basically you can take your dB co of this sort of derived complete intersection stack for the local model at least, and you can convert it to some question about the derived category of singularities on some hypersurface, some derived, some hypersurface stack. And And on that side, you can define window categories, et cetera, et cetera. And so the way that you globalize this is how do you, so let me just one sentence here is that the globalization, you figure out yeah, so the basic picture is that there's this technique called linear causal duality where you replace this presentation with a different presentation as a category of singularity. So dbco mod perf, and that's very, very close to being smooth. And so you can sort of import all of the stuff that I was talking about with this paper with Steve and Sam in the linear setting, just the smooth linear quotients where the of a quasi-symmetric representation, and you can sort of import that to define window categories and so forth in these categories of singularities. And now the question is, how do you glue that? Because this is just a local model. So only locally can you identify this with some category of singularities for some, use this linear causal duality. And so the real key idea in this D-equivalence paper is to sort of identify categories on the original side that correspond under linear causal duality to what the window categories are locally. And so that's basically the idea in a nutshell. And I'm happy to go. I guess you do GatherTown after this, so I'm happy to go into more detail if people have questions at some point. But that's the idea of how the window categories work. Okay.
Yeah.
Thanks.
And are there questions? Further questions?
Dan?
Yeah.
So the window categories were defined in terms of certain weights.
Yeah.
And so I'm not sure I understood what you were saying this about these intrinsic categories in deco X, but is that because like kind of these weights are defined globally and not only locally, or is that not?
Yeah, the point is that the weights are defined, the weights are just like a pointwise thing. So somehow that will be automatically a tall local over that really just happens in a single fiber. So you have a fixed point, you have a point and a GM in its automorphism group that is going to happen over a single fiber of the good moduli space. So that description of weight categories, the way I formulated it, will automatically be sort of a tall local over the good moduli space. So that's what's so nice about it. But the real question is, what's the weight category in this case? And basically, if X and X is a closed point, like you can there's a sort of map, say let's say with residue field C, then there's actually a map spec of C adjoins H1 of LX let's just see. Mod. So if it's a closed point, GX is reductive. And so you get a map like this. To X, and this is like, so basically there's I'll call this X reg. And now, so this is like a little nilpotent thickening of the point. So for every point in this quasi-smooth stack, you can, if every closed point, you can thicken it up a little bit by basically it's basically the universal first order thickening of that point. And you get a map like this. And then the weight condition says that X reg star of F, the homology of this, just as a representation of GX, should lie in a certain polytope. In the weight lattice of GX. So that's the flavor of the weight condition. So it turns out that you can cook up this thing, which is sort of intrinsic in the sense that I can just have my derived stack with a closed point, and I can say exactly what I mean for this complex to have the weight condition. And then the point is that when I go to the local model, it turns out that these weight conditions precisely pick out what the weight conditions are on the causal dual side. And so you know, that's how you know that these weight conditions are sort of the right ones that give you an equivalence. So the category of complexes satisfied these weight conditions restricts to be an equivalence for any generic stability condition. And so that statement, you can actually just prove that at all locally. But it's to show that the category glues to something global, it's important to have a characterization of this category that's really sort of, you know, a point-wise characterization of this category. So I can say, so I can define the category globally and then check that it's an equivalence locally.
You also need to define the functor globally, right?
Well, the functor is just the restriction functor.
Mm-hmm.
Yeah, so luckily, like derived algebraic geometry is at a point where, you know, like a derived stack just has deco, you know, the kind of usual functorialities and the usual derived categories. I mean, the stuff that goes into defining that is machinery. I mean, it's the theory of descent in derived algebraic geometry. So there's some machinery, but luckily all that stuff is in place. And so you do have a restriction functor from deco of X, right? So I should say at the end of the day, the theorem is that there's a category Wx of delta that sits inside deco of X, such that I have this restriction functor to deco of X semi-stable of L, and this is an equivalence for generic L and delta.
And do you assume the self-duality of the cotangent complex here?
Yes. So the theorem is that let me just make the oops. Oh. Okay. I don't know. My everything's collapsed, but basically the theorem is that for a stack that has a screen sharing stopped. Let me see. For a stack that has a good moduli space, a derived stack with a self-dual cotangent complex. Is this? Am I sharing again?
Yeah.
Yeah. So the theorem is that X is a derived stack. Derived algebraic stack. Lx isomorphic to Lx dual. And X classical has a good moduli space. And then L and delta live in the Néron-Savary group of X. So for any L, you can define the semi-stable locus. It's basically just with the Hilbert, you could just say it in terms of the Hilbert-Mumford criterion, a tall locally over the good moduli space, if you'd like. That's like the most concrete way to do it. So, so for L and delta generic. So this is the theorem. And so again, you're in the situation where the left-hand side does not depend on the class that's used to define semi-stability. So the left-hand side is sort of independent of semi-stability. It's a subcategory, and it's equivalent to the derived category of the semi-stable locus for any choice of semi-stability conditions. So this is like the true theorem here. And then it's a little bit of work to check that the variation of stability that you get from the Bridgeland picture actually fits into this framework. But you can take a non-generic stability condition, and then perturbing the stability condition, you can realize that as some class L in the Narron-Severi class, and the different neighboring stability conditions correspond to just different choices of the Narron-Severi class on the stack of non-generic semi-stable objects. So that I wasn't actually planning on talking about that per se, that just as a motivation, but this is actually the sort of the general theorem.
And do you expect a weakening of the assumptions by replacing this symmetry for cotangent complex by quasi-symmetry?
Well, I don't know what is so the symmetry, the quasi-symmetry. Yeah. So right. So actually, so I should mention that sort of based on this work. I mean, it like sort of a version of this was a preprint was out on my website for a while, and then based on that, Toda generalized this a little bit, and so he has a more flexible notion of the stack that's a little bit weaker than having a self-dual cotangent complex. But I'm not sure how much weaker it is. Yeah, the full. Yeah, I only actually use a very small piece of the. I basically the thing is self-dual. Locally, this looks like a. Right, it sort of locally looks like a self-dual. Well, I mean, it's mu inverse of 0 inside of V, and then mod G, where V is self-dual. That's the kind of picture that you end up. That's the local model you end up considering. Actually, though, the magic windows theorem is applied to, because under linear Causal duality you end up looking at V times G. Oh, I guess that's still self-dual. Yeah. So the only thing that actually comes up, the only instance that we actually apply. The only instance of the magic windows theorem that actually gets applied is the self-dual case. So yeah, it's just a special thing. I don't know how to. Yeah, it's a funny question. I never even thought about it. I can't remember why I just did self-dual cotangent complex. Oh, I remember. I mean, yeah, there's a step in the linear Causal duality thing. Like this sort of equivalence here. There's a step in this that uses the fact that it's a weak co-moment map. Yeah, so there is a step here that uses, it's not in this equivalence, but it's when you pass to the semi-stable locus. So the linear Causal duality, you take basically something in V, mu inverse of 0 lies in V, but now you're trying to say what are the semi-stable points, and then you want to compare that to the semi-stable points in V times G. And the question is, in general, they're not the same. You can have additional semi-stable points in V times G whose underlying point in V is not semi-stable. And so, but that doesn't happen in this co-moment. That doesn't happen in this co-moment map situation. At least it doesn't happen. You use the co-moment map to sort of deal with some of the subtleties about studying semi-stability, comparing semi-stability on this side of casual duality and semi-stability on this side of casual duality. So that's why it's restricted to the self-dual thing.
Okay,
can I ask a quick question, please? So when sigma is not generic, when you get a singular moduli space, could it be that, or maybe that's part of what you're talking, that you can you put a derived structure on the singular moduli space to make them all derived equivalent?
No. You can put a singular structure on the you can put a derived. There is a sort of canonical derived structure on the moduli space. Because like locally, it's like spec of some CDGA monoreductive group, and then you can just take the ring of it. You take the G invariance of that CDGA, and that's again will be a CDGA. So there is a canonical derived structure on the good moduli space, but it won't be equivalent to either of the resolutions. Yeah, I think what you're thinking of, right, is a sort of non-commutative resolution. So the question is there a non-commutative resolution of the singular thing downstairs that sort of interpolates between them? And these window categories basically play the role of those non-commutative resolutions. So the window category is just some kind of DG category that sits over the singular guy. And it's a sort of, that's like the natural thing, the non-commutative resolution. And then there are these canonical comparison isomorphisms with all the commutative resolutions. So I think that maybe the window category itself is the non-commutative resolution.
But actually, I think in Spenko and Vandenberg paper, they had an actual sheaf of algebras.
That's right, yeah. So basically, in the smooth case, you can take this window category, and it's generated by a tilting bundle. And so you can just take they take the endomorphism algebra, and you get some non-commutative sheaf of algebras, which is truly, in a very, in the Vandenberg sense, a non-commutative resolution. Yeah. So, there's like, as you know, there's different kinds of non-commutative resolution. So sometimes it's a category, and sometimes it's an algebra.
But does it work in the setup of your theorem, or does it work only locally?
Does what work?
A construction of a sheaf of algebras like that.
No, yeah, that only works locally, because how, well, I mean, maybe it works globally. I don't really know, but the literal construction that they do uses, like, you literally take the representations whose characterized in this window, and you take the direct sum, and then you take the endomorphisms and the G invariant of the endomorphisms, and that's your sheaf of algebras. So they actually, yeah, so, but it's a little bit more flexible than that. I think Spenko Vandenberg, I think that they do general resolutions for the, whenever you have a good quotient. So basically everything arising in kind of GIT, it will only be crepant. It'll only be crepant in this quasi-symmetric case. And that's the case when you can, like, then you have to be a little bit more careful. There's like a very specific algebra that they write down. So I don't know if that works. I can't really recall. But yeah, I do think that they get sheaves of algebras. Typically, yes. So maybe you could do that here too. I just haven't thought about it.
Dan, can I ask another question?
Sure.
So I kind of can imagine how you're, use the cotangent complex to, have this local description of your derived stack. But also in the magic window theorem, the cotangent complex was coming up in the weights that were bounding the things. Can you give a sort of intuition how the cotangent complex comes up in that setting?
Well, yeah, I mean, so that's, I mean, only kind of. So the magic, when I say magic, it's a little bit magical to me too. I don't really fully understand what it is about. So one of the interesting directions in this whole thing is like, yeah, what are the good window categories that are out there? So the quasi-symmetric case, there's the Schwenko-Vandenberg windows. That's not defined at all in terms of cotangent complexes or anything like that. That's basically like a combinatorial. They arrived at that via some sort of combinatorial algorithm that said that, hey, it turns out that the derived category, this wasn't how they formulated it, but this is how we reformulated it, that the derived category of the semi-stable locus just happens to be generated by vector bundles whose character lies in this window. So that's the Schwenko-Vandenberg thing. It's almost like it's a discovery. It's like a pure discovery. It's like, check it out. There's this algorithm. You start with all vector bundles that generate the derived category of the semi-stable locus. And then you can find relations between vector bundles via an algorithm, and to show that you actually only need vector bundles that sit in that, whose character lies in this polytope. So that's like the Schwenko-Vandenberg. So that's one way that the window condition comes from. And there it has nothing to do with the cotangent complex. But on the other side, well, I mean, maybe, so on the other side, there's a more general picture, which is that you have this stratification, this Kempnes stratification of the unstable locus, and you use sheaves supported on the strata to push in a more functorial way to take any complex and push it so that its weights along the stratum lie in some window. And there, the smallest you could possibly, the structure sheaf of the stratum, any sheaf supported on the stratum, if you look at its weights along the stratum, you'll pick up the wedge powers of the normal bundle of the stratum. So if you take any sheaf that's set theoretically supported on the stratum, there's a minimum possible window that the weights of that sheaf can sit in. And so, and that's dictated by that's controlled by the normal bundle of the stratum, which is basically where the cotangent complex comes in. So if you look at it from this perspective where you have this unstable strata, and you start with some complex, and you systematically take cones with basically copies of the structure sheaf of the stratum, then the smallest you could ever push, the smallest window you could ever push the weights into has exactly the width of the weights of the structure sheaf of the stratum. You can push no smaller, or else you'd start to get weights on the other side. I don't know if that makes sense.
I see, thank you.
Yeah, and so in that's where the cotangent complex comes in there. It's controlling the width. What's the smallest possible width you could squeeze your complex into by taking cones with things that are supported on the unstable locus.
Cool, thank you.
Mm-hmm.
Can I ask a question? So what about the D-equivalence conjecture for Calabi-Yau fourfolds? Is there some hope to
fourfolds?
Yes.
I don't know. I mean,
now this thing. I mean,
yeah, I don't know. Well, I mean, how many I don't know. I really don't know. I mean, how many fourfolds come up in this way? So I mean, I don't know that the window can, yeah, I mean, the two things that are missing are, first of all, control over the MMP, like you have in this sheaves case. And then second of all, you need, some really nice, variation of stability pictures to connect the different flops. So I don't think either of those are really in place for fourfolds, other than the ones that arise. This covers some birational equivalence classes of fourfolds, sits from this picture, but the general thing I really don't know. It's possible that the window techniques will still be useful for the general conjecture, but like down this line, this is, I think, as far as I can push it. I think like I need some new ideas for how to apply window techniques to like more general flops. Yeah. Yeah. Right. It's unclear how you could even start to prove this general version without something else about the MMP. I don't know. You need some kind of input. Yeah, that you have singular varieties popping up, and I don't know. It seems very subtle. Yeah. Sorry if you hear the screaming. That's just my baby. He's okay. He's just like, it's just normal. Okay.
So maybe at this point we should move further discussion to the gather town, if assuming Dan is still available.
Sure.
I think Aaron just posted the link in the chat down, I don't know, wherever the chat is for you. That's where the link is.